start this afternoon. Pleasure to introduce Daniel Duggar from Purdue, who will give the first of his 3 lectures on Voevodsky.
All right, first business is getting this working. Everything okay?
Yeah.
All right. By the way, I'm used to projecting a lot when I talk, so if it's just too loud, let me know. I don't want to scare you all off. A couple preliminaries. First of all, I'm not really an overhead kind of person, so I'm going to be trying to use the blackboard. I've tried to arrange it so that I won't write below this line, and so maybe you'll all actually be able to see what I'm doing. If there are problems, be sure to let me know, and I'll do something for the next 2 lectures. The second thing is the title. Voevodsky theory was what was suggested to me, and I was too lazy to change it. I might not have actually chosen it myself because the material I'm talking about is due to a lot of people. Voevodsky, Freeland, Sussman, Morel, a lot of people. The title I might have chosen was Mechanical Theory. Or what is not the same thing, homotopy theory of algebraic varieties. So this amounts to what is really a very ambitious program of taking all the methods that we have in algebraic topology and basically importing them, everything, into study of geometric problems. And it's very impressive. It's amazing that it all works. It's still at the very preliminary stages. So what I hope to do over the next 3 days is to give you some idea of what's going on. I find myself, well, in a little bit of a quandary in that I feel like there are 2 types of people in the audience here. On the one hand, there are certain people who don't necessarily know anything about algebraic K-theory or one-type cohomology or things like that, and just want to have some general idea of what's going on. And then there are people like Blaine and his students and that area working on algebraic cycles and who are working on very related things. And what I would hope to do is to, give them some guide to these papers so that they can see how close, the stuff they're doing is to what these other guys are doing. And be some kind of guide if they want to go read those papers. So I hope to do both. If I'm not, you should yell at me, ask lots of questions, do whatever is necessary to slow me down, because I really do want to spend the next 3 days having you guys understand stuff, not just me coming up here and going through my own program. It doesn't matter to me what we get to in the next 3 days. I'm happy to do my first lecture over and over again until things make sense. But okay. So what's the homotopy theory? It might be a little bit better to say what we're doing is stable homotopy theory. I'm going to add that word. Because what this basically is the study of cohomology theories. That was good. Light. So what the main application of this whole material is understanding various things about cohomology theories for schemes, or I'm going to keep saying that word scheme. I always mean algebraic variety. It's the same thing. So, I want to understand the cohomology theory of algebraic varieties and their relations, the relations between different ones. So to begin with, let me just start by putting up with you. Most of this is just sort of name dropping, and you're not going to understand it at this point, but I will define things over the course of the next few days. If you have a scheme, well, one invariant you can attach to that are the child groups. So you take algebraic cycles on your scheme and you identify them if they can be conformed to one another, modeled by rational equivalence. And there are other published relations you can mod out by. There's also algebraic K-theory. So you take algebraic vector bundles over X and take a Groton-D group that gives you K-naughts and do various other things to get the higher K groups. There are things called Milnor K-theory. Again, I'm not going to write down the definitions at this point. I just want to get their names up here. This is something very concrete written down in terms of generators and relations mostly. Actually, that's mostly defined when you have a speculative field. but let me just leave that up there now. There are atomic homology groups. Complicated things like that. L is a prime in this world. So some kind of fancy sheaf homology will be cooked up. There are algebraic gram homology groups. And there are motivic homology groups. So, I found motivic. And lots of other things. I could go on. I've written it in this funny way because these things are all kind of similar. They all sort of behave like singular cohomology. This is called K-theory, but that's for historical reasons. It's not really an appropriate name. This should probably be called the Muller cycle groups, if we could go back and rewrite it. So these are kind of like singular cohomology, and this is really something different. This is like complex K-theory. And while I'm up here, I write down, in some sense, the main achievement of this program so far, which was Voevodsky's proof of the mirror conjecture. So this is now a theorem of Voevodsky. And what that said is that two of these things, defined in very different methods, ended up being the same. So it said that if you have spec of a field, not something that maybe you really want to think about doing geometry for, but it turns out to be useful to do that. So there's a spec of a field, and the characteristic of F is not 2. Then Milner cooked up a map from these Milner K groups into the atomic homology groups. You want 2 coefficients. That should be lining out by 2. So kill 2 times everything. This thing is some fancy cohomology group. It's really just Galois cohomology. You have spec of a field. And Milner conjectured that this was an isomorphism. And so that's now a theorem. So what it's saying is that this thing, which is defined explicitly in terms of generators and relations, which I haven't told you, but it's very easy to write down, and this thing, which is defined in some complicated way in the atomic homology, sheaf cohomology, and some funny Grothendieck topology, end up being the same thing. And the way that you see that they're the same thing is you end up comparing them and see that they're both pieces of motivic cohomology. So these are the kind of questions that come up into this field. You have all these different cohomology groups. There are lots of different conjectures about how they relate to each other, how various things relate to motivic cohomology, how motivic cohomology relates to algebraic K-theory. Lots of these questions have been answered now, but that's what this theory was designed to tackle. Now, once the basic theory is in place, you can go on and ask other questions. They're a bit more esoteric. But there are signs that they're interesting answers. One thing is that as soon as you have some kind of world where you can do anything you do in algebraic topology, then you can basically make any cohomology theory you want. Okay? There are these guys, but now you have the ability to construct lots of new cohomology theories. The main one that has received attention at this point is algebraic comordism. People are just starting to understand this. The other thing you can do, and this is what the topologists are loving, is that you can take any question you know in algebraic topology and ask it in this new world of algebraic geometry. And so one question is, what are the motivic stable homotopic groups of spheres? This is not just daydream at this point. There's a definition of what stable homotopic groups of spheres are. No one knows how to compute them. Okay. No one even knows how to compute the stable pi naught. Okay, there's a conjecture for what that would be. And I'll talk about that probably in the third lecture. But there are lots of kind of neat open questions at this point. All right. So let's go back and talk more about this. Quantific homotopy theory is a funny phrase in some sense. What you're doing is taking one scary word, which connotes a lot of machinery, and another scary word with a lot of machinery, and putting them together. Well, that's no good. So I think that my job in these two talks is to somehow be your guide through what's going on here. And in particular, I'm a homotopy theorist. So I'm going to be talking about things really from this perspective and trying to do my best to make it understandable. So part of what I need to do over the next 3 days is give you a crash course in homotopy theory. And I'm not going to do this all at once. I'm going to do little pieces here and there. If I did all at once, you'd all get up and leave, because it would be very boring. But right now, what I need you to understand is just some basic examples of what it means to do homotopy theory. So the first one is just topological spaces. And that's the most familiar. So what happens when you do homotopy theory here? Well, of course, you have a notion of homotopy classical maps. And from that, you get a notion of homotopy equivalence. And the most basic goal is to understand spaces up to homotopy equivalence. Except that's not quite what we do. So what turns out to be more important, and which you learn at some point in your graduate career, is that most of the spaces that you really care about, manifolds, things that come from manifolds, classifying spaces, can be built from basic things, from spheres and disks. So most spaces of interest can be built from cells. So in this case, I mean spheres and disks. My writing big enough, by the way? Can you guys get back read this? So, for example, it seems silly to give an example, but if you take the projective spaces, RP2, then what do? You take a one cell like that, and what am I thinking? So you take the times 2 map from the circle to the circle and you cone it off. So it's a one cell with a 2 cell added onto it in a funny way. And the way an algebraic topologist would draw this is the following. We use these little circles to denote cells. There's a 1 cell, there's a 2 cell, and it's been attached in some way. It's been attached to the times 2 map. So that's a little picture of RP2. As you go up, well, you take RP2, and then you attach a 3 cell, and then that gets attached some way. That's RP3, and then you have some more pictures. RPN has 1 cell in each dimension, various attaching maps. And the algebraic topologist's job is to understand these attaching maps, and then to use those to prove things about the spaces. Maybe one last example. If you had a torus, how do you make a torus? Well, you take 2 1 cells, alpha and beta. We'll put them here. It's in dimension 1. Then you take this 2 cell, and you glue it to this 1 cell around the boundary using the usual picture. So I've added a 2 cell up here, and it's attached on it in a funny way. So in homotopy theory, what happens in all these examples I'm about to give you is that you're very interested in how to build spaces in terms of more basic things. Here are the most easy examples. only interested in cells and what they tell you about spaces. But this is how you get all of your topological invariants that you know. Singular cohomology, these are computed by distributed time cell decomposition. Homotopy groups come from mapping spheres in. Somehow, the algebraic gadgets that you know that tell you things about the homotopy of a space all are based on cells in some way. So what we do in practice is that we don't try to understand homotopy equivalence. We try to understand sort of the parts of homotopy equivalence that you can see by using cells. So what homotopy theorists usually study is a notion called weak equivalence, or weak homotopy equivalence. So the definition is so weak homotopy equivalence if only if it induces isomorphism on all homotopy groups. For all indices, all base points, this kind of thing. So you're using cells to map in and see when two spaces are the same. It would be equivalent to say that maps from A to X, A to Y, is an isomorphism for all cellular spaces A. Cellular spaces CW complex, same thing. So you're studying the portion of homotopy seen by these basic objects. This is going to come up a lot later on when we start doing homotopy theory for schemes. And the cells are going to be all algebraic varieties. And we're going to see how you can build things in terms of algebraic varieties. And that's where I'm going to show the equivalence will come. No. In fact, if A is finite, this equivalence is not true. Okay. For this equivalence to be true, you need to involve all infinite dimensional A. In fact, the theorem is that, the problem is that this pointed versus unpointed. If I made these pointed and did this, then you can use finite things, I think. All right. So that's the first example. Let me give you the second example we need. So here R is going to be a ring. And we're going to look at the category of chain complexes over R. Here, you still have the notion of chain homotopies. So if you have two chain complexes, chain homotopy classes. And you have basic objects, so your basic cells, are denoted R bracket n. What this means is the chain complex with R in dimension n and 0 everywhere else. So this is the chain complex which has R up in dimension n, 0 everywhere else, and of course there's no room for boundaries. Boundaries are all 0. If you try to compute homotopy classes of maps from one of these basic cells into a chain complex, that's just another name for the homology of your chain complex. So let's just do it real quickly. There's a chain complex. What does it mean to give a map? Well, the generator here has to get some element. That element has to go to 0, so that's a cycle. Yeah. A is a chain complex, so this is your chain complex there. Do you mean what are the R ends? The A ends are modules over the ring. Chain complexes of modules over R. I feel like I'm losing you. Yeah. Everything should be dotted. These are all chain complexes. Does that help? Maybe. So here you have a module. Think over invariant groups. So R is Z. You have an invariant group in every dimension. You have a differential. So to give a map of chain complexes, that generator has to go to somewhere. It has to be a cycle, because it has to commute. And then when you mod out by chain homotopies, chain homotopy means you're killing boundaries. So you get cycles mod boundaries, which is the homology. So I want to draw your attention to the analog here between homology of a chain complex and the homotopy groups of the space. They're both computed in the same way by mapping in certain basic cells into your object. All right, so then a map of chain complexes is a weak equivalence, usually called a quasi-isomorphism, if it gives you isomorphisms on these kinds of objects. So, if that's iso for all. So I'm just saying it gives you an isomorphism on homology. And there's one last thing I want to say about this example. Suppose I'm going to just take a module, an R module. Think of it as a chain complex by putting it in dimension 0 and having nothing in the higher dimensions, lower dimensions. It's a very trivial chain complex. Now when you form a free resolution of this module, what does that mean? So you take a bunch of R's, map it there, so it's surjective. Take the cardinal, put a bunch of more R's, map that in, like that. And this is a quasi-isomorphism by the way you've constructed it. So what you've done is you've replaced your object by something which has been built from cells. 0 cells, 1 cells, 2 cells, and so on. So free resolutions are really the same thing as CW approximations. All this is very basic and can be made much more precise than I'm doing, just showing you the examples. There's a general notion of model category, which all this stuff fits into. I might talk about it next time. We'll see. There's one last example, and then we'll move on to more interesting stuff. The last example is superficial sets. So this one I'm going to breeze through because I only need it because it will come just a little bit later. But a superficial set is a bunch of sets, x0, x1, x2. So the xi are sets. And they're connected by various maps. So you have 2 maps down, 3 0, 3 maps down here. So you're supposed to think about it just some combinatorial data. It's like a superficial complex where you're allowing a little bit more freedom. And let me just give you one example. Suppose I wanted to that space. So I have 2 0 cells, 2 1 cells. As a superficial set, well, the 0 cells are A and B. The 1 cells, I have C and D. Those are the interesting ones. I also give myself what are called degenerate cells. So I imagine taking a 1 simplex, that line, collapsing them all onto that one. So I have sort of a form. So it's strange because the light on this thing seems to be off from the on.
Now? Yeah. How about if I just talk loud? It looks like that's good. Okay. All right. Yeah. All right. So I need to talk loud and write things. Yeah. Well, get this. All right. So, sequential sets, you're supposed to think of it as instructions for building a space. Tells you what the symbols are and how they're attached to each other. And then there's a notion of weak equivalence that comes up. It's all kind of complicated, but it was realized in the 50s that you can do homotopy theory using this kind of combinatorial data. And I won't write down the definition, but what I need you to know is that homotopy theory of sequential sets is equivalent, whatever sets homotopy theory is used, to the same thing for space. So if you want to understand anything in homotopy theory, ordinary topological spaces, you can use the geometric category of spaces, or you can use this more combinatorial construction. This more combinatorial construction is mostly useful because it interacts very well with category. Okay, we're going to see. Sorry to say it. All right. So those are the basic examples I need you to have in your head. Now that we have all that basic stuff, we're ready for more modules. Quite a jump, huh? So what I want to do here is tell you what modules are in topology. Okay, and that will be very easy to understand. And then I'll describe what this was in Algebraic Theory. So the first story is topological. So inside the category of all topological spaces, topological recurring groups. Something's beeping. I think this thing may be battery. It's possible. I just turned it off. Okay, so you know what a topological group is. I'm just trying to show you. All right. So, what are some examples? You don't know what you can see. So, any discrete abelian group. Let's start with trigger. There's S1. What has a group structure given by perfect? I'll think of it as so there's S1, and there are tori, the product units. Those might be the only ones you can think of off the top of your head. It turns out basically they're only finite dimensional. But there are lots of extra dimensions. Take on for time. What that is in space, homotopy is A dimension n, zero everywhere else. These are big infinite dimensional cell complexes, but they can be constructed to have a recurring group structure. And the reason they're important is that they homotopy classes of that. So we say that singular cohomology theory theories and abelian theories, because it's represented by an abelian. Now, there are also lots of others. Given any space X, you can take the free abelian group on X, the free abelian group on the points of X. So most likely your space is uncountable. This is some huge thing. You can do it. And you want to topologize this in a certain way. So I won't go into details here. It's not that hard. But for instance, if you have a sequence emerging to X infinity, then your space X. Another sequence Y infinity. Then you want the formal word, let's say, n X I plus n Y I. We'll use brackets to the formal. Right? Then you want that to converge to X infinity plus n. And sensible things like this. So these things all give you infinite dimensional topological variables. And what this is also called is the mode of X. Probably I should stick the word unstable in here. Let's not worry too much about this. Unstable mode of other space. An important theorem here is called Mach. Empty sometimes. Is there are two things, however. One is that the homotopy groups of this new object are the homology groups of this space. And the second is that, let's see, every topological group is a product of those autonomous things. Up to recount up. So what the second thing is telling us is that the homotopy theory of the topological theory of groups is pretty easy. They all decompose into other domain spaces, which is simple things to understand. So we're looking at here. What this is telling us is that the organization of X, the modum of X, somehow capturing the singular cohomology. In fact, what's going to happen is that the modum of X somehow has all the information in it that singular cohomology can have. That's all it has. There's no real advantage here. But right now I'm trying to build up your intuition for what's going to happen in algebraic geometry. The advantage there is that you don't have a single cohomology, which tells you everything in this world. So I will answer your question, I promise you. But I find it hard to answer right at this moment. That seems fair.
Well, I mean, you're doing us a lot of sort of graph definitions and complicated things, and they just said, well, but it's equal to something we layer with all our lives.
Yep.
Then, why should we be motivated to?
Well, all I can say
They're
is,
so complicated you're not even defining them.
right? All I can say is wait for the lecture, and then you don't have to come back. No, I absolutely think you're asking a fair question. I don't mean to do that at all. But I don't think I can answer it until I just tell you some more. Yeah.
What aspect of the life X and which property are you saying?
Think of it as the motive part.
Yeah. I mean, which aspect that you're focused on is that
the organization. All right. Okay, trying to actually line this up here. Yeah. What is the motor part?
Yeah, what's the mistake aspect?
Okay.
Is it just that it's, I mean, you say carrying cosmology and cosmology and then that
Sort of still in the category of very like space. It's thrown out a lot of information.
Right, exactly.
yes.
So here's the category. Yeah. Here's all topological spaces. And here are the modes, which are their going groups. Topological. The spaces in here only have information which can be detected by single cohomology. What we're doing is we're taking the whole picture and pushing it down into the small one. It's easier to understand. And that's the aspect we're doing. Exactly. Yeah. Exactly. So what I was going to say next is actually related to this. I'm just making this, well, not even making full science. But let's say this. The cohomology theory is the billion. And it's not really a definition, but the only thing it seems about x is the mode of x. So let me write it like this. So if it has the property that whenever m of x is equivalent to m of y, then d star of x. Yeah. M of x, the mode of is the going dimension. So then the theorem, sort of a restatement of this, is that the only abelian cohomology And the proof is very simple. Any cohomology theory is represented by some spaces. If it's a billion, those spaces actually are going groups. Therefore, they decompose from here. Projection? No, it's not a projection. You know, x is even different from x. So it's not a projection. You're definitely you're going further and further down. All right. So now we come to this point over here, which is why you would care about this. Because, in fact, the homotopy theory of topological invariant groups turns out to be equivalent to this homotopy theory of chain operating groups. And the usual name for the mode of x is the single chain. And this can all be made very normal. So there's nothing really new here from what you've been doing all along. It's a different way of picturing it. And now what's the good from this new picture? Well, the good is that you can apply it to lots of other situations. So this is a bit of a side, but let me just say it. This whole perspective I've just given you is to the He is using it for a very specific purpose. what he wanted to do is attach to any commutative ring homology. It's supposed to be the analog, so for associative rings, it gives you a Hawkshire. For commutative rings, there was supposed to be a corresponding view. He was trying to figure it out. So what he did is he took the category of rings, then did some special rings. He wanted to be doing some kind of homotopy. And then he did exactly this story. So inside here, you have the Abelian group objects in simplicial rings. So this is simplicial rings with an extra Abelian group structure, are compatible with me. We have a drawing contours if you'd like to think about this. So these are the modas. This is the motivization attached to simplicial rings moda. And by studying this picture the same way that we did here, you can take a simplicial ring, take its motivation, take its homotopy rings. Okay, and that's homology, not cohomology. Take that. We can also do cohomology. So this was a perspective where this is an application where this viewpoint actually did provide some human use. It's not very fun for a moment. It doesn't. So you can also do it for associative rings, but the notion of what this category turned out to be is different. So when you talk about Abelian group objects in associative rings, that's one thing. You talk about Abelian group objects in commutative rings, that's something else. You get different modes. If you do it for ordinary rings, this is a process to come out. It's a special ring. So we have a ring in dimension 0, a ring in dimension 1, 2 mapping out, 1 map out. The same thing as a special set, except the other ring. Say that again? Master ring. Yes. All right. Any other questions? Almost done. What do we have? 2 more minutes?
Was this something to show wrong people were so unhappy? How you can see that a 2-cycle translates into a map series?
Next time we're going to be doing that all out. All right. So, yeah. Yeah, exactly. It's much more complicated. Yeah. So in fact, if you take, here's a good example. So if you take the sphere, you take this motor. Well, let's do it this way. So if you have a point in space, space with a base, then to that you can attach the reduced mode, which is where you take the motive of x, and then turn that base point into 0. So the homotopy groups of this reduced motive are the reduced homology. So let's do the reduced motive of Sn. The homotopy groups are the homology groups of Sn reduced. So you only have something in dimension n. I star equals z star equals n. 0 elsewhere. So this is precisely now we're in Planck space. So the reduced motive of Sn represents singular homology. If you do the motive of Sn, then you get something which has homology of atoms in the plane space. And this is very complicated. This has all the information from scalar algebra. Like that. So you're right. These are very, very complicated. Other questions? All right. So let's go now to algebraic geometry. And now I can show you why these forward. Yep. That's on your viewpoint. It's getting rid of information. Where I wanted to write down this picture.
Well, I mean, but part of your simplification, what happens if you keep on taking new?
No, I mean, so the motive of the motive is already very complicated. been figured out over the last 20 years in topology is that things that go on in stable homotopy theory break up into certain levels. What's phenomena? This is a very big picture. It's not just that I'm being pictured, it is all phenomena. Break up into very stuff. This is called the chromatic tower. So at level 0, you have, we're going to do the cohomology theory. So you have singular cohomology theory and a train. Very cool. At level 1, you have trade theory, relocation, things like that. At level 2, you have elliptic cohomology. Then way up at level infinity, you have complex subordinate. That's what feeds everything. And then in between, so I think we'll put this on gravity. The cohomology theory is sort of resemble complex theory. Detect higher level.
So this is our properties like gate theory, homology, Chicago, or some of the other ones.
Pretty much, yeah. So you're detecting more information as you go up. So down here, this is what motive are. Motive are encapsulating the stuff about space, about homotopy theory, which can be detected using this theory. And then there's a lot of others. So it's not so much that we're really simplifying things, but that we're fractioning out a certain kind of information. If that's the correct way. I'm running out of time, so I need to get out of here. So in algebraic geometry, I told you that there were these various homology theories. So you have the Childers, you have Child homology, these are all like singular cohomology. These are all sort of abelian theories. Here's what I mean. It's capturing this level of phenomena. So Grothendieck got the idea of trying to take all the stuff that you were detecting in these theories and find some universal cohomology theories to all of them. So if you want to find universal universal abelian cohomology. I'll add all that information. Usually we're out to $2 worth of day. That's what we do. So what I want to do is say, look, what he's really looking for is this category of motives that we've defined. So what he really wants to do is take the category of algebraic varieties, have some kind of abelianization now. And what it lands in is the category of motives. And what you really want to do is understand the homotopy. Yeah, exactly. And now it's complicated. So what happened here was that every space could be built from cells. And what that translated into was that the motive of the space broke up into parasimbolic domains. So I didn't say this very, hold on, let me continue just a second. I didn't say this very well. But this cell did an algebraic bank space. Since it hasn't been built from cells, what turns out is that the motive of it breaks up as a polygon. Not just these, but these and those. And lots of stuff. What's happening here when you do geometry is that it's not possible to break your algebraic varieties up into compactable cells. Yes, it's going to work for Gauss line, for projector spaces, those kind of things. For some arbitrary algebraic variety, there's lots of geometric information in there which can't be decomposed into little bits. So the category of motives is much, much more complicated. sure, will happen. But not in general. So these things, trajectory would be very, very helpful. So there was a question. Oh, right, that's like a little fun. All right. So let me spend the last 7 minutes just telling you a little bit here. So the thing is that what growth deep 1 is not quite what it's been done. Right.
Yeah.
So what's going to happen is that right now I'm going to tell you a little bit more about what's expected. And then next time in the second talk, I will actually construct this thing for you. Show what kind of axis it has to satisfy. Pretty much, yeah. Pretty much. I won't say axis. I think you'll be happy with it. I mean, this is not just going to be right. Yeah. Yeah. Well, come back and see. That's all I can say. All right.
So what are you saying this problem hasn't quite been solved yet?
No, it hasn't.
Hasn't.
It hasn't solved. What I'm saying is that Grovedig's original idea will not come.
But there is a correct.
It seems like, yeah, I think everyone's pretty happy. The reason for doing all this and doing this stuff is that when we actually develop the properties of this category, that intuition is going to just make everything so easy. But, all right, let's just imagine now that we have this guy. We can do some kind of homotopy. Geometric theory. So, given any two objects, x and y, we can look at the following. Take 1 over x, 1 over y, and we homotopy across the maps. And there's one other thing I'm going to go into the mix. The category of modes should be triangular. So, any space x, let's go back to topology, any space x has a suspension. And you can do this in the category of mode groups too. Chain complexes have a suspension by just shifting the chain complex up. Any place you do homotopy theory, you have a suspension operator. So I'm going to throw out a suspension operator in here. Single line. Part of the triangulation. So we have these various groups. If this were topology, then the mode of y would just break up into a bunch of unordered K spaces. This would just be some kind of singular topology of x. Here you should think about it as being some kind of quotidian homology of x, but now with coefficients in y.
Oh, I don't understand what.
Yep. Did you understand that?
So you're looking at maps.
Homotopy classes of maps in this fictional
X, MY, modulo.
modulo.
Okay, that I understand.
Okay. Now what I'm saying is that I should have told you this before, but anytime you have a homotopy theory, you have a suspension operator. So in spaces, it's this picture. You take x, form 2 cones and move them together. Called a suspension.
Right, you expect to see that there's such a thing.
For any homotopy theory, there's always such a thing. So what I'm saying is that we're going to make a homotopy theory of modes. There will be such a thing. And that's what I mean. If there's not in the category of algebraic varieties, you're going to have to expand the category. So we're going to have groups like this. Now there's this was topology, M of y would just be a bunch of ordered angles. This would be particular homology. This is a more complicated version where I actually have working out y.
Where's the I?
Well, it's going to be the ith degree. Coming to the gradient of the logic. All right, almost. So, okay, let me just say over here. we're at the point now where we want to take the category. Okay, let me back up one more step. So this is the category of modes. What I want to say is that, so what people have been trying to do is produce all these connections, produce the connection between two different homology theories. So the Werner K theory and the topological homology. So he's trying to detect something in this stuff, which sounds pretty typical. People had done this in low dimensions, and what had basically happened is that they were using information from up here. What Voevodsky realized is that to prove this equivalence, to prove the Werner conjecture, he had to use information from arbitrarily high levels. He had a program for doing this, using these ramifications that he could make. So he finds himself not wanting just to have a category of modes for Algebraic chapter, but a whole homotopy theory. So there's a very specific application that he was trying to do. Alright, so what we're going to do is take algebraic varieties, and we're going to embed it in something much bigger. So as you've been objecting, algebraic variety doesn't really have a suspension. It's also true that if you have an algebraic group, you can't really make a class of that and stay in this category. So these are going to be sort of our basic sets. And then we're going to allow ourselves to glue things together in all kinds of funny ways. So the picture you should have is that these are your atoms. And now we're introducing some new glue. We're pushing them together. And the glue is really topology. So you have geometry in your atoms and topology in your glue. And they're getting mixed up. So this is going to be what's in the homotopy. Inside here, we're going to have the abelian part. And these will be the ones. So what I'll be able to do next time, and everything's going to get much more specific. So those of you who have been very happy might be more happy. But given all this information that I've given you today, I'm going to tell you how to make the category of modes. Another video I'm going to tell you how to make this. And we'll talk about, as you asked, what kind of actions it has to satisfy, what are the important properties that